Alright, so here are some work solutions to the IB Chemistry 2016 May Paper 1 SL. This will be part 1, so we'll look at the first 10 questions. Alright, let's have a look at question 1. Question 1 was, which equation represents sublimation? So sublimation is not a chemical process, it's a physical process, so a change in state. So because it's not a chemical process, we shouldn't be making or breaking new things. So anything where we see new substances being made, bonds being broken, we're going to rule those out. So we can rule out A and we can rule out D. Now sublimation is going from solid to gas, and so that's why B would be the correct answer, because we can see here we're going from solid to gas. So we need to look at our states, whereas in C we're going from gas to solid, so that's desublimation. So B is correct because we're not looking for desublimation, we're looking for sublimation. Sublimation is going from solid to gas. So B is the correct answer for question 1. Question 2 was, for which compound is the empirical formula the same as the molecular formula? So to work this out, we need to figure out what the molar mass for the empirical formula is, and then if it is the same as the molar mass for the molecular formula, which is given to us, then that means that the empirical formula and the molecular formula is the same. Now in this on this paper, they gave us the relative atomic masses, so they told us that hydrogen was 1, the relative atomic mass of carbon was 12, and oxygen was 16. Alright, so using those values, let's work out the answer to this question. So I'm just going to zoom us in a little bit. So we'll start with A, looking at CO2H. So carbon is 12, or relative atomic mass is 12. The relative atomic mass of oxygen is 16. There's 2 of them, so we'll do plus 16 times 2, or plus 32. And then hydrogen is 1. And that's going to give us 45. So 45 obviously is not equal to 90. So the molar mass for our empirical formula is 45. The molar mass for our molecular formula is 90. So the empirical formula and the molecular formula is not the same for A. So A is not correct. If we have a look at B, it's going to be 12 plus 3 plus 16. That's going to give us a value of 30. It's not equal. Let's have a look at C. We've got 24 plus 4 plus 16. That gives us 44. So that's not right. And if we have a look at D, we've got 12 times 4, which is 48, plus 8 plus 16, that equals 72. So that means that D is the correct answer because these are equal. So the answer for question 2 is D. Let's move on to question 3. The question was, in which mixture is sodium hydroxide, or NaOH, the limiting reagent? Now, in order to determine the limiting reagent, we first need to know what is required of us. So we need to know the chemical equation. So we can see that there are 2 chemical equations going on. We've got NaOH plus sulfuric acid. And then we've also got, for C and D, we've got NaOH and nitric acid. So we need to figure out those balanced equations before we can figure out what the limiting reagent, before we can figure out which option sodium hydroxide is acting as a limiting reagent. So let's start with NaOH plus H2SO4. NaOH plus H2SO4. So H2SO4 is sulfuric acid, so we should know that's an acid. NaOH, well, that would be a metal hydroxide. So we need our acids and bases principles, which tells us that sodium hydroxide, or a metal hydroxide plus a base, is going to give us salt and water. So to form our salt, we need the positive ion from our base, which is Na+, and we need the negative ion from our acid, which is SO4 2-. So you need to remember your polyatomic ions. So we combine those together to get our salt. So it's NaSO4. However, because we've got 2-, that means it needs to be Na2SO4. And then obviously water is the other product, so plus H2O. If we balance this, we see our sodiums are not balanced, so we'll pop a 2 out here. And now we pop a 2 in front of this one here, and that should be everything balanced. Let me double check that. So we've got 2 hydrogens plus another 2, that's 4 hydrogens on the left. We've got 4 hydrogens on the right. Oxygens, we've got 2 oxygens on this side, 4, so that's 6. We've got 4 plus 2, that's 6. So 6 oxygens on both sides. And our sodiums are balanced. Alright, sulfur is obviously balanced, we made no changes there. So that's our balance equation. So that means the ratio of our reactants is we need a ratio of 2 sodium hydroxides to 1 sulfuric acid. Oh, I just realized I popped a plus there. That should be a yield error. But so this is our reactants ratio or reagent ratio. So we need 2 sodium hydroxides for every 1 sulfuric acid. So let's have a look at our options. A, we've got a 2-to-1 ratio because we've got 0.2 to 0.1. So that works out, that checks out. So A is not the correct answer because we're looking for when we don't have enough sodium hydroxide, or when sodium hydroxide is a limiting reagent, which looks like it'll be B, because we see here we've got a 1-to-1 ratio when we're supposed to have a 2-to-1 ratio. So therefore, in B, our sodium hydroxide is our limiting reagent, so that's our correct answer. Alright, let's move on to question 4. Question 4 was, why do gases deviate from the ideal gas law at high pressures? Well, ideal gas law assumes that the molecules themselves do not take up space. So if we have a look at what that means. So if we have a look at the gas here in this container and we fill it up. So there's 20 particles or 20 molecules of gas in here. So if we want to find the volume of that this gas takes up, we can just calculate this volume here and ignore this space that each individual molecule is taking up because it's negligible. So the volume of each individual particle is negligible. However, if we now reduce the size of this container, so reducing the size is obviously going to increase our pressure. We still draw 20 molecules in there, so 1, 2, 3. Now, because of this, we can say, okay, let's calculate the volume of this by having a look here, but it becomes more problematic to ignore the volume that each individual particle is taking up, because now that we've got this smaller space, or we've increased the pressure, the effect of the finite volume of those molecules is now more obvious. So that's why A is the correct answer. Bit of a tricky one. Question 5. Which is correct for the chromium isotope, where the mass is 53, atomic number 24. So which is correct? So this is going to give us the amount of protons. So we need 24 protons. And then this number here, the atomic mass, is going to give us the number of protons plus neutrons. Whereas the atomic number just gives us the number of protons. So if we want to find the number of neutrons, we need to subtract this number. We need to subtract this number from this number to get the number of neutrons alone. So 53 minus 24 equals 29. So we have 29 neutrons. So we need 24 protons, 29 neutrons, which is, careful here, C. So not B. B says nucleons. We're looking for neutrons. Nucleons refers to protons and neutrons. So this, yeah, those would be our nucleons. We don't have 29 nucleons, we have 53. So don't get confused there. So for question 5, C is the correct answer. All right, let's have a look at question 6. So question 6 was, which electron configuration is correct for the following ion? Se2 minus. So with electron configurations, what I like to do is I draw up this little diagram. So you go 1 to 7. So 1, 2, 3, 4, 5, 6, 7. Then you do that again, but not 1 to 7, it's 2 to 7. So 2, 3, 4, 5, 6, 7. Then you do 3 to 6, 3, 4, 5, 6, and then 4 and 5. So it should end up looking like this sort of a play button, a triangle. And then in the first column, they're all S's, S, 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 S. Second column, they're all P's, so P, P, P. Third is D, and the fourth is F. And what I like to do is I just go from sort of this way, so along this way, and whatever I encounter is how the order in which I write my electron configuration. This way, got one S. So we know that S's take up 2 electrons. Next, if we go this way, the first thing we encounter is 2s. Once again, S's are 2. Then if we come down again, we've got 2p, then 3s. So 2p, 3s. P's are 6. S's are 2. If we come again, doing the arrow, we've got 3p, 4s. So 3p, 6, 4s2. Move this over. If we come down like this, we've got 3d and then 4p, and that's where we're going to stop. 3d, 4p. Why are we stopping at 4p? Well, if we come up and have a look at what we're looking for, which is SE, it is in the 4th period, so that's 4. It is in the P block, so that's 4p. So we know it needs to end in 4p, which is why we stopped there. If we come back, the d orbital occupies 10, or takes 10 electrons. Alright, so we can rule out whatever doesn't have 3d10. I can already see A and B are not going to be correct because they've got 4d10 in the second last position. And it's going to be 4p6 because we've got the 2 minus ion. So it's not going to be 4p4, but it's going to be 4p6. So that's why D would be correct. So question 6, D is the correct answer. Alright, let's move on to question 7. So question 7 says, which of the following is a metalloid? So we come back up to the periodic table and get rid of my other markings. So metalloid. So we need to draw in the staircase. Start from boron, draw the staircase in. Whatever is directly above and below the staircase, except for aluminium, is going to be a metalloid. So above, below, above, below. So remember, that's everything above and below the staircase except for aluminium, which is a metal. So if we have a look here, what were our options? Go back down to the question. It looks like it will be B. B will be the correct answer, because if we come up here, let's get rid of my marking for a second, but we see arsenic there. Arsenic is a metalloid. So come back to the question, B, arsenic. Question 7b is the correct answer. Question 8. Which periodic trend is described correctly? Well, let's have a look at atomic radius. So atomic radius, when we're going down the group, is going to increase, because as we go down the group, we're adding on an electron shell. So that's obviously going to increase our radius. However, when we go across the period, the atomic radius decreases, not increases. And that's because even though when we go across the period, we've got the same amount of electron shells, so we're not adding electron shells, but we are adding additional electrons as we go across the period within the same shell, but it is one more electron, which means the attraction of that shell towards the nucleus is stronger, because we've just made that shell essentially more negative in simple terms. So that's why across the period, the atomic radius is going to decrease as that shell is being sucked in closer to the nucleus. So A is not being described correctly, because this should actually say decreases. Trend for ionic radius should be the same as atomic radius, so this is also not described correctly. So ionic radius also increases down the group and decreases across the period. Let's have a think about electronegativity. So what I like to do is just think about fluorine. So fluorine is the most electronegative. So if we come up to the periodic table, let me remove my previous markings. Essentially what we can do, locate fluorine. How do we get to fluorine? So across the period, that means electronegativity is increasing. And coming up to fluorine this way, electronegativity is increasing up the group, which means that it is decreasing down the group. So as we go away from fluorine, electronegativity is decreasing. So the trend there is that it increases across the period, decreases down the group, which I think was what they said there. Electronegativity decreases down the group, yep, and increases across the period. So D is the correct answer for question 8. Having a look at question 9, which molecule is non-polar? So we need to draw in Lewis structures. So if we have a think about A, so we've got oxygen with 1, 2, 3, 4, 5, 6, fluorine has 7, 1, 2, 3, 4, 5, 6, 7. So if we have a think about this, because of the lone pairs, this is not going to be a linear structure. It's actually going to be sort of bent in shape, so it'll look like this. Fluorine is the most electronegative, so we're going to have electrons being pulled this way. So that's going to leave a slight negative charge on this side, whereas it's going to leave a slight positive charge on this side, so that is definitely polar. So we rule that out. A is not correct. We're looking for the non-polar one. Let's have a look at B. So we've got nitrogen. So nitrogen has 5 valence electrons. So 1, 2, 3, 4, 5. Hydrogen has 1. So this is NH3. Once again, because of this lone pair, it's going to have a bend in the shape. So if we think about it sort of like a pyramid where we have nitrogen on top and hydrogen out like this. Nitrogen is more electronegative, so pretty much all our electrons are going to be pulled that way, leaving a slight negative charge up here and slight positive down there. That's definitely polar. So B cannot be the correct answer. Let's have a think about C. So got BF3, so boron in the center. I remember boron is happy having either 6 or 8 valence electrons. So in this case, it's going to settle for 6. So boron has 1, 2, 3. We think about fluorine having 7, 2, 3, 4, 5, 6, 7. Another one. 1, 2, 3, 4, 5, 6, 7. Another fluorine. 1, 2, 3, 4, 5, 6, 7. No lone pairs here, so if we have a think about the shape, that's going to be trigonal planar. So just like this. Fluorine is the most electronegative, so it's going to pull this way, this way, this way. So those dipoles are going to cancel each other out. So that's why C will be nonpolar, because even though we've got dipoles, they essentially cancel each other out. So if I draw that for you like this, so that's, oops. So if I draw that for you like this, it'll essentially look something like that. So those dipoles cancel each other out, which leaves the molecule as a whole nonpolar. So C, BF3 is definitely nonpolar. Alright, and the last question for this part is, which compound contains both ionic and covalent bonds? So this requires some good understanding of our polyatomic ions, because polyatomic ions are where we have a positively charged thing and something negatively charged, but rather than just being something that is simple like Na plus and Cl minus, we've got polyatomic compounds, so there's covalent bonds between them. So for example, the ones you should know for positive is NH4 plus, so that should do for positive. For negative, we've got CO3 2 minus, we've got NO3 minus, we've got PO4 3 minus, we've got OH minus as well, got SO4 2 minus. So these are some polyatomic ions we should have memorized. So anything that contains either of these any of these compounds is going to have a covalent bond and also an ionic bond. So let's have a look. So if we have a look at B, we've got NaNO3. So what we've got there, if we break that down, NaNO3 is we've got ionic bonds between the positive Na plus and the negative NO3 minus. So that's the ionic bond there between these two. And then we've also got a covalent bond in here between our nitrogen and our oxygens. So hopefully that explains that. So question 10, B is the correct answer. So that's all for this part. Happy studying.